We looked at our binomial distribution yesterday. But a binomial distribution, I guess it's discrete, isn't it? Because you've got a lot of series of points. We want to turn it into a continuous distribution. And the normal one is the one we like working with because we can standardize it and get our answers out. So that's what we're going to attempt to do. So let's start with this one. We're going to estimate the probability that a school of 1,200 students, much like ourselves, contains more than 150 left-handed students. So what's the probability? So I guess the question is, how would we solve something like that? Well, we could take a large sample. The example I've used here is 50 students, work out how many left-handed students are in that sample, and then use that experimental probability to then make a conclusion about the whole school. So let's say I did that, and in our group of 50, there were 8 left-handed students. So therefore, I'd estimate the probability of being 8 out of 50, 0.16. So probability of being left-handed is 0.16. So then I can put it into binomial probability. So X is going to be the number of left-handed students. We're interested in this. We're now saying, well, it's binomially distributed. There's 1,200 students, so that's the number. Probability of success is 0.16 based on our sample that we took. We want to know probability X is greater than 150. Well, when you're thinking about it, that's a lot to work out. 151, 152, 153, 154, 155, all the way up to 1,200. A lot of calculations. So we're going to use the complementary idea. Problem is with something like this, there's still a lot of calculations because we've got 0, 1, and so on up to 150, end up 151 different calculations. Now, I wasn't silly enough to use a calculator for that. I used a spreadsheet. So I did actually work it out. It turns out to be 0.9996. But clearly, that's not a practical way of doing it. The polygon ends up looking like that. So if we were to draw it in. So what we just found, remember the probability is the area under the curve. So we just found the area to the right of 150. It's basically what we just found. But look at this distribution that I've just drawn. The mode is somewhere in the middle. It's symmetric. And when we look at the frequency graph there, it tails off very quick and at the front too. So it has that classic bell shape that we saw with the normal distribution. So because it looks like a normal distribution, then we say, well, maybe it's fair enough to assume it's a normal distribution. Well, let's turn it into a normal distribution. If we had assumed it was normal, okay, well, the two important pieces for normal distribution was the mean and the variation. That's what we wanted to know. We saw that it's binomially distributed. There was 1,200 students, and from our sample, we said the probability is 0.16. The mean, then, of that data, n times p. So it'll be 192, we're saying, is the mean. The variance, np, 1 minus p, will be 161.28. So there's the two pieces of data I'm now going to put into the normal distribution. So I'm now going to say it's normally distributed like so. So 192 mean, variance of 161.28. But now we can standardize that data. Okay, remember our little formula for finding z-scores? The random variable minus the average divided by the deviation. So we wanted to find x is greater than 150, and we said it's going to be easier to do the complementary event. So 1 minus probability of x is less than or equal to 150. But now I will standardize that 150. So it becomes 150 minus 192 over the square root of 161.28, which is minus 3.31. We can then look up our table of values and come up with our answer. You'll notice it's not exactly the same because we're approximating. But I tell you what, it's pretty close. We got 0.9996 before. We've now got 0.995. In fact, it's out by a factor of 0.008%. So for this particular data, it worked really well. So the question then becomes, when is it okay to approximate using the normal? How will we know whether, this is going to work? This is going to give us a good approximation. Right? There were three key things that I looked at when I looked at the curve. The mode, we want to be somewhere in the middle of the data. We want it to look symmetrical, and we want to see that tailing off, so we get that classic bell-shaped curve. That's what we're looking for. I'm now going to bring up some different binomial distributions. Here's one where probability of success is 0.125, and the different curves I've drawn in there were for different number of times we did the trial. So 10, 20, 30, 40, and 50. So the question is, which ones, if any, would be okay to say, yeah, that looks like a normal distribution. It's got those features we were looking for. So here are the things that I'm looking at. Probability of success, and obviously probability of failure. But I'm also looking at NP and N times Q. And over in the right column, I'm deciding yes it is or no it's not. Now for these ones, 50, I'm going, yeah, that's okay, because I can see on the left-hand side it is starting to do that tail. I'm okay with that. 40, I'm up in the air about, so I've put both a tick and a cross there, because it's starting. But the ones before that, the graph chops sort of up on that rise, so I don't think that's good enough. We're not seeing the tailing that we want to see. So for that one, I'd be comfortable with 50 if we were doing 50 trials. 40, starting to stretch it a bit, maybe between 40 and 50. So that's probability being 0.125. 0.25, the graph would look like that. So now I'd be comfortable about 30 onwards. 20's getting close. 10 definitely not. Probability of 0.375. Now they're really starting to come out. And I'm pretty happy with all of them other than the first one there. And when it's 0.5, bang in the middle. Yeah, okay, even the 10 now I'm starting to go, yeah, okay. Now, we don't want to draw them every single time. This is why I put in the NP and the NQ column, because I'm looking for what did all the ticks have. And so as a general rule, I'm just looking for this. If NP is greater than 5 and NQ is greater than 5. So you can see with this one, 10, it was bang on 5, and that's where I'm going, yeah, it's close. And I think as soon as both of those get over 5, then I'm happy. Just a general guide there of when we go, yeah, okay, we could do a normal approximation here. So what we're actually doing, remember, is we're approximating the area under the polygon with the bins. That's just the numbers, if you remember. And ours are 1 unit apart. Now, the polygon, if you think back to the histogram, remember how the histogram, you joined it up to half the next, well, before and half below? So it's really that integral that we're finding. When there's very small samples, they have this thing called a continuity correction. And so instead of saying between A and B, they go, well, A minus 0.5, so they take it to that minus 0.5 on the integral and the plus 0.5. Now, don't get too hung up with continuity correction. If they want you to use a continuity correction, they'll tell you. If they don't mention it, just forget it. Forget about continuity correction. All right, so last year's HSC, particular bias coin is tossed. So actually the probability of head in this case is 3 in 5 rather than 1 in 2. Coin's tossed 100 times. So X is going to represent the number of heads that we get. And we're told it's going to have a binomial distribution. Okay, find the expected value. Well, it's binomial, so N times P, we get 60. Makes sense, probability is 3/5, I'm tossing it 100 times, I'd expect 60 heads. Now, by finding the variance, show the standard deviation is approximately 5. I think they were nice here by doing the show bit, because if you didn't get the standard deviation, at least you can go and do the next parts of the question. So variance, NP times 1 minus P, we get 24. Standard deviation is, of course, the square root of that. 4.8989. Yes, that's around about 5. And I think the way they've worded this question, I'm definitely writing down the 4.898979 bit, so they know I just didn't go, oh, look, yeah, that's fine. At least I've said, yeah, look, I found the number. Now they say, righto, let's find the probability, but we'll do it using a normal approximation. It's got to be between 55 and 65. It's binomially distributed at this stage. Number of trials is 100. probability of success is 0.6. We're going to turn that into a normal distribution where the mean is 60 and the variance is 24. Standardize it. So now, and look at the numbers that came out very, very nicely. And that's why I think they said show it's approximately 5, because now we don't actually need our table of values, because all they're really saying is, one deviation either side of the mean. The z-score is going between -1 and 1. So we can use that empirical rule, and the graph is even on the reference sheet, so you read straight off it. So we know that would be 0.68. 0.68. Okay, there's our first part.